Listen, I may or may not have a lot to live for. I don't know. I'm only 8.
Don't look directly into even the weakest of UV lights.
Oh, the space banana. Whoa! Oh no! Oh, this is how it ends.
I very genuinely love learning and doing new things and being very hands-on in the process. So join me as we walk around and find out.
Welcome, friends, to the Black Hole Tour. I'm your tour guide, Astra. We have a beautiful day here on TRAPPIST-1e, so thank you for spending it with us and choosing Space Expedition. We know you have a lot of options for tour companies here in the year 2395, and we truly appreciate you choosing us.
It's 2021, idiot.
2021? Well, that means you've traveled in time, so that doesn't make sense. Time machines weren't fully developed until 2250 and were banned in 2249.
My dog could write better jokes than that.
Anyways, we are going to be visiting a few different kinds of black holes today. We're going to start with visiting stellar black holes before investigating the intermediate black holes. Then we're going to space vault to the center of the galaxy to look at a supermassive black hole before returning here to TRAPPIST-1e safe and sound. How does that sound, everybody?
Like a waste of time.
Perfect! I'll initiate the launch sequence and start us on our way. Today, we're going to look at different kinds of black holes, the theories behind them, and why middle schoolers are the worst. Welcome to Bad Astra.
As a child with an unspecified age between 11 and 13, I take full offense to that part.
Fine, let's get some science content.
Why?
We need to talk about polyamory.
Remember when Pluto was demoted to dwarf planet?
It's okay, man. We all make mistakes.
Isn't physics fun?
Is this being recorded? Let's take a quick refresher on black hole anatomy. There are a few main parts to a black hole. The singularity of a non-rotating black hole is the infinitely small point with a huge amount of mass, usually the remains of a long dead star, that warps space-time to make a black hole exist in the first place. Then, there's the event horizon, located at the Schwarzschild radius for non-rotating black holes, which is the point of no return. This is the distance from the singularity where the force of gravity becomes so great that nothing can escape, not even light. The Schwarzschild radius is also the boundary where Oppenheimer and his co-authors thought time stopped. Remember, gravity warps both space and time. Now, time only appears to stop to the outside observers, not in the perspective of things falling into the singularity. But it's theorized that past the event horizon of a black hole, time gets weird. Cause no longer precedes effect. The past doesn't determine the future, and time travel might be possible without those silly time machines that were banned in 2249. Now that we've covered non-rotating black holes in detail, and several other videos, I should point out that most black holes do rotate. This is because the original stars were rotating, and almost every object that falls into a black hole wasn't falling directly in, but was caught passing by and spiraled in. Angular momentum is conserved, which means that all that spinning doesn't go away, and thus the singularity rotates with the leftover spin of its star corpse and that of every meal it's ever eaten. For rotating black holes, this anatomy is a bit more complicated. The singularity is actually an infinitely thin ring. The event horizon for rotating black holes is actually closer into the singularity than the Schwarzschild radius, and isn't even a sphere. Because the singularity is a ring, the event horizon appears oblong, squished at the poles and bulging at the equator. Now, if that weren't weird enough, rotating black holes actually have two event horizons. Remember how we said that the event horizon was both the point of no return and the shell where time stopped? Well, for non-rotating black holes, these two things happen at the same distance from the singularity, the Schwarzschild radius. But for rotating black holes, these distances are no longer the same. So you get an outer event horizon, which is the point of no return, and an inner event horizon, or Cauchy horizon, where linear time breaks. Rotating black holes also have another fun region surrounding them. Because the black hole is really massive, warps space, and rotates, they actually drag space itself along for the ride, in a creatively named effect called frame dragging. This frame dragging creates an ergosphere, or whirlpool, inside which every object, even light, is forced to rotate along with the black hole. It's like a fun dance party, but without consent. Remember that all of these are mathematical constructs based on the theory of general relativity, and any object going slower than the speed of light would reach its own point of no return much further out than the event horizon, its own whirlpool farther out than the ergosphere, and as for the timey-wimey Cauchy horizon, no one really knows because they banned time travel back in 2249. A black hole's shadow is essentially the event horizon, but not quite. The light that passes close to the black hole and eventually makes it to your telescope is gravitationally lensed by the black hole itself. So the resulting shadow, what observers see, is actually a bit larger than the event horizon itself.
It looks like a butthole.
I can assure you it does not function like a butthole.
Ha! You said butthole! Ha! Butthole.
There are moments when I miss live theater. This is not one of them. Back to science. Theoretically, you can create a black hole out of anything, as long as you compress the mass small enough to create a singularity. For example, you could take a grape, condense its mass into a singularity, and boom. You'd have a black hole that is warping spacetime as much as the mass of a grape would. However, while physics says that may be technically possible, you will not have the strength to make that a reality.
Oh yeah? Watch me.
No, there's no food allowed in the spaceship. No, please don't do that. You'd literally have to compress it orders of magnitude smaller than the size of an electron.
Die.
Well, while that child is occupied, now is a great time to talk about the usual circumstances in which black holes form. Stellar black holes are usually created when a star dies in a Type II supernova, or core collapse supernova. These stars are between 8 and 50 times the mass of our sun, and near the end of their lives they run out of fusion fuel and suddenly collapse under their own weight, causing nuclear reactions which release an incredible amount of energy. This energy, combined with the outer layers hitting the hard surface of a newly formed neutron star, causes this collapse to rebound and blow off the outer material in a massive stellar explosion. If the original star was less than 20 solar masses, the remaining material will probably form a neutron star, held up by neutron degeneracy pressure, the force of neutrons pushing against each other as the remaining star becomes a single atomic nucleus. However, if the initial star was between 20 and 50 times the size of the sun, the mass of the remaining material will likely be so great that gravity will overcome even this pressure and collapse into an infinitely small point, or singularity. Please note that these ranges are generalizations. There are a lot of other factors at play besides a star's main sequence mass. For more information on that process and the life cycle of stars in general, check out our first video, Even Stars Must Die, or our recent clip, Stellar Black Holes. The important part is that the outward pressure of neutrons pushing against each other cannot overcome the inward force of gravity. In addition to stellar mass black holes, there are supermassive black holes at the centers of galaxies, which have been observed by astronomers. Intermediate-sized black holes have been observed through gravitational wave astronomy by the LIGO and Virgo detectors. They were probably formed from the mergers of stellar black holes, but astronomers aren't really sure, and there may be unknown physics at play. So further study is needed.
So the astronomers don't even know why they exist? I feel like if anyone should know, it should be the astronomers.
Science is all about finding answers to the questions about how the universe works. And often we're still working on finding those answers. Even though they're smart, often scientists come to the wrong conclusions, or only figure out part of the solution. So they have to change their minds on things later on, when they get more data, or someone comes up with a solution that better fits the data. And part of what scientists do is poke holes in each other's ideas, double-check each other's analyses, disagree with each other's conclusions, and reject each other's papers. Thanks to scientists questioning and arguing, our understanding of the universe is constantly evolving. Not as fast as it could be, thanks to Reviewer 2, but I guess even they are an important part of the peer review process. Just because scientists change their minds doesn't mean they are lying or giving you fake news. This is just how science works.
Oh, like how Pluto isn't a planet anymore?
No, shh, shh, shh. Please don't talk about that.
Why not? Why? Why?
Why? Why? Why? Why? Why? Why?
Why not?
If you mention Pluto one more time, you might summon Eris, and that will derail the entire black hole tour.
Oh well, now I'm just gonna have to talk about Pluto. We're gonna have a Pluto party right now. Gonna be sharing some Pluto info, mofo.
No. Supermassive black holes, the biggest butthole-looking things in our universe!
Hell yeah.
These are the black holes typically found at the centers of most galaxies, anchoring them with their massive gravitational pull. Astronomers don't know how they form, but one idea is that these black holes might be the result of a ton of stellar black hole mergers. In a dark sky, you can see the galactic plane of the Milky Way galaxy, and in the constellation Sagittarius, there is an apparent bulge, which is the collection of stars and light in the inner 10,000 light years of the galaxy. When you look at the bulge, you're looking towards the black hole Sagittarius A star at the center of our own galaxy.
I've seen better bulges. Am I right, ladies?
First off, that's heteronormative nonsense. Secondly, where are your parents? Thirdly, the Milky Way bulge is the best bulge and the only one I have ever found any joy looking at. There are many different types of black holes. Non-rotating and rotating, stellar mass, intermediate mass, and supermassive, roaming black holes that could sneak up on an unsuspecting planet at any given time, and some theorize that there are quantum entangled black holes, which are connected somewhere at the bottom.
Could we get swallowed up by a roaming black hole?
It's an absolute possibility. But we have gravitational sensors, which keep our ship safe as we tour through the galaxy.
But could we still die?
Yes, we can if we get too close. Let's continue on.
How would we die?
Well, it's a bit gruesome and kind of horrifying to think about.
I want to know every step, in detail.
I don't see any adults whom I can ask permission to tell you this, so I'm going to continue and blame any incurred trauma on your own curiosity.
Hey, I'm my own individual. I can make choices for myself.
Curiosity killed the cat.
And satisfaction brought it back.
Touché. Let's talk about the death of science, Tommy. For any massive object, its gravitational pull is stronger closer to its center of mass. The Earth, or our current planet, TRAPPIST-1e, technically warps space more on the surface than in orbit, so satellites feel slightly less gravitational force than people. However, this effect is really small, since the Earth isn't supermassive, and the closest you get to the center is still pretty far away. However, since a black hole has a huge amount of mass in a very small space, you can easily get close enough to the center of mass for this difference in gravitational force, or tidal force, to be deadly. When Science Tommy got a little too close to the black hole, the tidal forces did a fun thing called spaghettification. The gravitational force felt by his head was way stronger than the gravitational force felt by his feet. This meant that his corporeal form got stretched into a long, thin piece of human spaghetti. For him, time passed normally, and his death happened quickly and painfully. For everyone watching in this horrifying situation, we saw him slow down and freeze at the event horizon. We saw him get ripped apart, atom by atom, slower and slower, longer and longer, until he froze at the event horizon, mid getting ripped apart. We watched for a while, but his remains stayed there, suspended in frozen time. The warping of space-time by the black hole stops your time from the observer's perspective. So, the only visible piece of you left is a mirage, the only evidence that you ever were alive in the first place.
Why does the man in the video look like me?
I don't know. Why does that man look just like you?
That seems like a strange way to grieve. Or a threat.
Maybe it is. Maybe it isn't. Maybe this is just a way to encourage you to stop interrupting the tour with your jokes that are obviously a desperate attempt to make your peers think you're more likable than you really are. Anyway, all of these space and time dilations that you would experience from your previous life's death can be explained by Einstein's theory of general relativity. If you want an in-depth look at that, check out our previous video on the subject.
Why is this tour filled with ads I can't skip?
General relativity. It's not an ad. I just can't be bothered to go in depth when I already have.
That's what she said.
Well, at least that joke wasn't heteronormative. So, black holes were predicted by the theory of general relativity long before we actually observed one. But we'll get into the observations in next week's tour. Suffice to say, even way back in 2021, we had both gravitational wave and optical observations of black holes. The main problem with black holes is that they also involve quantum mechanics, which is completely incompatible with general relativity. As much as scientists want them to end up together at the end of a beautiful romantic comedy, they're just too different, and the Hallmark Channel hasn't responded to our script submissions yet. General relativity has an explanation for everything in the universe on a large scale, and is the friend that will always ask you to text them when you get home safe, even if it's still light out. They have their 3 equations that organize the universe in the perfect platonic ideal of a bullet journal. On the other hand, quantum mechanics has just woken up from a night of intense binge drinking and gambling and has no idea where all the electrons are, even though tiny things are their entire responsibility. Then, all of a sudden, they'll find an electron, but it's one that suddenly began to exist with a positron buddy and is not at all the one they were responsible for the moment before, because the ones they were in charge of went off, met positrons, and annihilated each other. And in their hungover state, quantum mechanics just throws up their hands and lets the electrons in tiny parts of the universe do whatever they want because their organization involves a napkin from a karaoke bar called the Ursa Minor Key with incoherent numbers and symbols scribbled in Sharpie and a dry erase pen that's completely dried out and has no cap. The problem is that both theories share joint custody over black holes due to some massive plot device in the romantic comedy that never gets explained throughout the course of the film. The event horizon is the big part that general relativity is in charge of, but the singularity that is smaller than anything imaginable is quantum mechanics' responsibility. And then string theory just showed up and is claiming that both are irresponsible parents and that it should be the guardian, and oh my god, it's just...
So where is this contrived B-plot going in this stupid romantic comedy metaphor?
Black holes are incredibly massive, so general relativity should be in charge. But they're also infinitely small, so we need to give custody to quantum mechanics. For now, the court awarded them joint custody, and it's a mess. Also, since even light can't escape a black hole, there's no way to know what's actually going on past the event horizon.
We ain't found star.
Theoretical astrophysicists request grant funding as further study is needed.
Boo! Is there anything that doesn't require further study?
Not really when it comes to black holes, but there are some interesting things we can explain the majority of, like when a black hole dies.
Black holes can die?
Everything dies, Science Tommy.
That's not my name.
Is it not? Huh. So, Hawking radiation is the displaced mass that comes out of a black hole that leads to its eventual evaporation. The universe follows conservation of momentum and energy, for the most part. On average. Okay, sometimes it makes an exception for quantum mechanics. Okay, it makes a lot of exceptions, but only little ones. Quantum mechanics says that two opposite particles, like a positron and electron, can sometimes just appear out of nothing and then almost immediately crash into each other and annihilate themselves. Yes, we're breaking conservation of energy, the first freaking law of thermodynamics, but only a little bit for a very short time, so it's totally fine, right? The particles appear, party it up, and then meet back up and poof, annihilate each other like it never happened. Except sometimes when one of the particles falls into a black hole. Oops. Again, quantum mechanics is too busy getting blackout drunk most nights to really pay attention to what these particles are up to. Now we've got a spare particle hanging out and the universe is coming home soon. How do we fix the energy of the universe? According to Stephen Hawking, that greedy black hole pays the price. Because that black hole took the party too far, it has to give up some of its mass, equivalent to the energy of the leftover particle. Remember that E equals mc squared, so mass and energy are basically the same thing. So, when the universe gets home, all the energy is still the same, just in a slightly different place. Which, the universe doesn't pay attention to the little things. In losing this mass, the black hole emits Hawking radiation, photons, and slowly evaporates. All black holes are slowly evaporating, and their days are numbered. Micro black holes can completely evaporate, but the evaporation time of stellar mass black holes is like 10 to the 64th years, way older than the universe itself. They're effectively immortal until they're not.
That makes no sense.
Welcome to the Black Hole Tour! We've got a long way to go, so come back next week when we go more into the black holes we've observed, how we observe something that doesn't emit light, and the technology being used and developed to help us learn more.
Will there be fewer ads on the next tour?
I'm going to pretend you didn't ask that question. Please remain seated until the spaceship has come to a complete stop. We hope you'll join us for part 2 of the Black Hole Tour next week. Remember, you'll go a reasonable distance with space expeditions. Astra out! Thank you so much for joining us here on Bad Astra. If you enjoyed watching, please like this video, leave a comment telling us what topic you'd like to see next month, and share it with everyone you know. Be sure to also subscribe and ring the notification bell so you never miss a new episode. And if you can't get enough of me, Eris, and Science Tommy, join our Patreon, where we post behind the scenes, deep dives, and other fun content. A special thank you to all of our Patreon supporters who make these videos possible. Astra out.